All right, hello and welcome back to applications for the class Rational Choice Theories. All right, so today we're going to talk about the difference between pure standard Nash equilibria and subgame perfect Nash equilibria. And the idea is that the concept of a Nash equilibrium may not be sufficient when we're considering uh, dynamics of the games or extensive form games. Okay? The idea is that there are going to be some equilibriums where some players are going to make threats, and these threats are not going to be credible. All right? So let's take a simple example to illustrate this. So we're going to have two players. And here we're going to add some details. We're going to consider that player one is kind of the entrant to some market, right? They want to enter to get a piece of the pie of a given market, and player two is going to be called the incumbent. So they're already on the market making rents, and they don't want any more competition. And so here each player has two actions, also known as strategies, and they're going to play sequentially in the following extensive form game. So this game tree is what we call an extensive form representation. So first, player one plays at their first decision node, and they can choose to either stay out, right, or enter. If they enter on the market, only when they enter on the market is player two going to play, and player two can choose to either fight, denoted by F, or accommodate, denoted by A, right? So here again, this is the way we represent this simple game. Now the last element, now that we talked about the players, player one and player two, the action of each player, player one can either stay out or enter, and player two can either fight or accommodate. Now that we've discussed all of these things, the last element is going to be the payoffs of the game. And so here, for each potential outcome, we assigned a pair of payoffs here, which denote the first entry is going to be the utility of player one, and the second entry is going to be the payoff or the utility of player two, right? So here, what does this mean? This means that if player one stays out of the market, player one is going to enjoy a payoff of 0, while player two is going to be able to accaparate all the rent of the market. And this is going to be 4. So player 2 gets a payoff of 4. Now, what happens if player 1 enters here, and then player 2 chooses to fight? If player 2 chooses to fight, the payoff are -1 and -1. The idea here being that they're very competitive against each other, and in the end, it's destructive more than anything, and it's making both players worse off. If player 2 chooses to accommodate, they simply share the rent equally. And so they get 2, a payoff of 2 each. Okay? So now that we have understood the basic structure of the game, typically you're more familiar with a normal form game or a matrix representation of a game. And here the matrix representation, typically we put player 1 as the row player. Player 1 can either choose stay out of the market or enter the market, and player 2 as the column player can either choose to fight or accommodate, right? And so here we have a 2x2 matrix, and here we can report the payoffs. And so here, if player 1 stays out of the market, the payoff is always going to be 0, 4. 0, 4. If player 1 enters the market and player 2 fights, the payoff are going to be -1, -1. If player 1 enters the market and player 2 chooses to accommodate, the payoff are going to be 2 and 2, right? So make sure you understand how I went from the extensive form game on the left representation to the normal form game representation. So these two representation don't have exactly the same meaning, because on the right, we do not have the sequentiality of the game, which is captured by our matrix. And here, typically, how do we solve these games? If we start with the normal form representation on the right, typically we fix the strategy of the player and we figure out what is best to do for each player. So let's start with player 1. Suppose player 1 believes that player 2 is going to fight. If player 1 believes that player 2 is going to fight, they're going to compare 0 and -1. And they're going to stay out because they don't want a negative payoff. So 0 is the highest payoff, so S is going to be the preferred option. That's if they believe that player 2 is going to fight. If they believe that player 2 is going to accommodate, they compare 0 and 2, and this time they'll want to enter the market because 2 is the greatest payoff, right? And we do the same thing for player 2 now. So if player 2 believes that player 1 is going to stay out, they compare the payoff of 4 and 4, and they're indifferent between fighting and accommodating. So they could either fight or accommodate. In both cases, they'll be alone on the market and get a payoff of 4. If player 2 believes that player 1 is going to enter, player 2 is going to compare -1 and 2. And here they prefer to share the proceeds of the market than to fight in a destructive manner. So they'll choose to accommodate, right? So here in this case, we have what we call 2 Nash equilibria in pure strategies, okay? So here we've only considered pure strategies, and the Nash equilibria correspond to the outcomes where both payoffs are underlined, okay? So here the 2 Nash equilibria in pure strategies, so pure strategies, are going to be stay out and fight and enter and accommodate. And so what is happening here? The idea is that if player 2 threatens player 1 to fight, player 1 will prefer to stay out, right? But if player 2 accommodates, player 1 will prefer to enter. So we have 2 Nash equilibria in this game. However, this game is not exactly what the most natural equilibrium we can think of, because this game does not take into account the sequential nature of the game. This normal form representation here. So what is wrong here? What's wrong is that the threat of player 2 is what we call non-credible. The threat of player 2 is non-credible. Why is it not credible? Because once player 2 is here, they'll never choose to fight, right? And so here we introduce the concept of backward induction. So if we were to solve for the game and to make sure that the game is sequentially rational, we would solve the game by backward induction, which means we would start at the end of the game tree, start with player 2 and say, if player 2 ever has to play once player 1 entered the market, they will compare the payoff of fighting, -1, and the payoff of accommodating, 2. And they'll always prefer to accommodate, right? So the threat of fighting will never work, because if they ever have to choose something, once player 1 entered, they'll choose to accommodate. And now, given that player 2 will always choose to accommodate if player 1 enters, then what player 1 has to compare between staying out and getting a payoff of 0 and entering is the payoff of 2. And here player 1 would much prefer the payoff of 2 to enter, right? And so here we will be left with a single equilibrium, which is the unique SPE of the game, the unique subgame perfect equilibrium. Which is the game that is sequentially rational the equilibrium that is sequentially rational for both players, and this will be enter and accommodate. All right. So by considering the dynamics of the game, we made the non-credible threat equilibrium go away, and we are left with a unique equilibrium. All right, that's it for today. Thanks a lot for your attention.